Hi, so today we're going to be going over how to create a shockwave within a 80% bell nozzle in the fluent simulation. So let's start with that and work our way through it. So we're going to use our existing fluent 80% bell design. I'm going to show you how to do the meshing and everything. As before, do a quick recap. Let's see, we're going to share a screen. Go to our workbench. All right, so right here, we're going to go zoom right in and we'll show our geometry. That's going to load up. We're going to zoom right into there. All right, so this is going to be our geometry. This is about half of the bell nozzle, and we're going to finish the rest of it using the symmetry tool to do the whole bell nozzle itself. But this makes our lives a little easier by doing half at a time and still getting the data for the full contours and velocities along the streamline, which we can measure right here at the symmetry. All right, so now that we have our shape, we're going to go to meshing, and I'm going to show you how to mesh. All right, here is the meshing screen. To mesh it, we're just going to go to mesh, and it's going to give you this. You're going to want to make it about 1 to the e to the negative 0.002 meters to make it more accurate. And then also go to insert face meshing, and then you want quadrilaterals, and do that, and it'll space it all out, and it should come out kind of looking like this, which is good. If it looks about this, it is accurate. You can make it smaller if you want to make it more accurate of the simulation, but for this, all we need is about that to get an approximation of what we want. Now we're going to exit out of here, and we're going to start set up our experimental procedure. All right, should be loading any second now. All right, there we go. I'll share it with you. There we go. There. Okay, so you want this. You want solver processes, double precision, and display mesh after reading. I hit start. It's going to load up our program, and this is going to be our main Fluent solver. All right, sweet. Should have loaded everything, and it's going to take a second to initialize all of our variables set up. All right, sweet. So first, we're going to make sure our models, we have energy selected on and viscous and viscid selected as well. And we're going to go to materials, go to fluid, air, and we're going to make sure that it's an ideal gas. You don't want it constant because it's going to be changing densities as it goes. Next, our boundary conditions. Make sure our inlet and outlet is all selected. We name these in the meshing process. This is your inlet, this is going to be your outlet, and then this is going to be your wall. And this is symmetrical, so it's going to repeat the same design over and simulate it as if it was symmetrical. Now, we're going to go to our pressure outlet. And previously, we had a pressure that was calculated to be about the exit pressure for the rocket nozzle, given the atmospheric conditions. But for this, we want to set our gauge pressure to about this number. And this should create a theoretical shock wave within the nozzle. So it's going to be like around this location of it. If you don't do this with the outlet, it's not going to create an outlet shock wave. So we're going to hit apply. That should be all good to go. And we're going to go to symmetry, make sure everything's all good. Now we're going to initialize. Initialize from the inlet. Initialize. All right, now everything's all good to go. We're going to go run calculation. I have it about 12,000, but it shouldn't take that long. Hit calculate, and we're going to wash the braces as it goes to calculate. Looks like our energy equation had a little bit of a moment there. There we go. Everything should have converged. We're going to check to see our contours. Sweet. All right, so this is going to be our new pressure contour. With the shock wave, it's going to be right about here, as you can see. And after the shock wave, pressure increases again due to the slowing of the velocity. Because once you hit your shock wave, it's going to reduce your velocity by a huge amount. That, and if you use the pressure tables, you can, or the shock wave conversion for a normal shock wave, you can calculate an approximation for the amount of pressure drop and temperature drop and velocity drop, along with Mach number. So once you hit this giant, what's it called? Shock wave, I'm so sorry, that you're gonna have a huge drop right there. Look at, next we're gonna show you how to do a plot. This is contour, and where you can do this for anything. I'll show you that we can do, let's see, we got pressure. We're gonna look at some velocity, show our velocity magnitude. As you can see, it drops off right here as well. If it was a normal shock wave at the exit, you're going to see it continuously increase. But since the shock wave's right here, it's going to drop off in velocity, and it's going to become a diffuser. And as you know, diffusers, you're going to slow your velocity instead of increasing it, like in the case of high-speed aerodynamics. So it's just going to keep dropping from here, except for around the wall. The wall is going to keep around the same velocity because it's not, it's kind of being funneled. All right, so I'm going to quick show you how to do a couple of the fun ones. Parallel properties. We're going to show you how to do speed of sound. As you can see, this is speed of sound. Now we're going to also do Mach number. Bam, that's your Mach number. If you want density, you can go here. And that's your density. All right, now for some plots. This is where you get your data from. I'm just doing a normal XY plot, and we're going to calculate the pressure right here. And it's going to be our static pressure from our symmetry point, which is our halfway point or mid-center line. We're going to hit plot. And this is what we're getting. So as you can see, the static pressure is dropping till we hit our shock wave. And once we hit the shock wave, it's going to jump up quite a bit, and then it's going to die off around the same amount, about 4.00 to e to the 6 pascals. So we can do this for everything else. Let's see, shots, XY plot. Yeah, density. Sure, it's on our symmetry. Save and plot. Bam, here's our density. and we want anything else. Let's say we want velocity along our symmetrical point. Let's save the plot. Bam, there we go. Anything else we would want? Let's say Mach number. Same thing right here. As you can see, the Mach number is increasing as it goes through the diffuser or rocket nozzle. But then once the shockwave happens, it acts as a diffuser and slows down the velocity. And we already did pressure. Anyways, let's do temperature real quick. As you see, there's a huge temperature drop as the pressure also drops. Then once the pressure goes back up, so does the temperature at the end here. It's more pressure, more temperature. And that'll be about it. I'm going to show you real quick how to use the post process. Also see a better image of the contours real quickly. So let me share, hit our results, and we're going to share that screen once it loads up. All right, so this is going to be our post-op. Just to get a better idea of how the contours look, we can go through this program and look through it. So you're just going to go here, insert contour, say it's velocity, type that in, and in this case I have this one. You make sure the variable is velocity, and you select it right here, and the number of contours. The more contours, the better, of course. So, and then select that. You see our velocity. So instead of 1/2, you can see the full image here. You get an idea of it. Sorry for that. X, C. And say we want to look at the right where the shockwave happens. Like looking right here, you can see the difference between the velocities as it goes through. And you can do this for any of them, as shown before with pressure. And we can switch over to that. This is going to be your pressure drop and then your temperature and density. Thank you so much. I hope you have a nice day. Hopefully I'll be better soon. Hopefully no more COVID. All right. Have a nice day. See you guys later.